Projective Geometry, Volume 1, by Oswald, Veblen, and John Wesley Young.
Chapter 7, Coordinate Systems in 2- and 3-Dimensional Forms. Section 69, Non-Homogeneous Coordinates in Space. Point coordinates in space are introduced in a way entirely analogous to that used for the introduction of point coordinates in the plane. Choose a tetrahedron of reference O, U, V, W, and label the vertices O equals 0 sub x equals 0 sub y equals 0 sub z, U equal infinity sub x, V equal infinity sub y, W equal infinity sub z, figure 84. And on the lines 0x infinity x, 0y infinity y, 0z infinity z, called respectively the x-axis, the y-axis, and the z-axis, establish 3 scales by choosing the points 1 sub x, 1 sub y, 1 sub z. The planes O infinity x infinity y, O infinity x infinity z, O infinity y infinity z are called the xy plane, the xz plane, and the yz plane, respectively. The point O is called the origin. If P is any point not on the plane infinity x, infinity y, infinity z, which is called the singular plane of the coordinate system, the plane P infinity y, infinity z meets the x-axis in a point whose non-homogeneous coordinate in the scale 0x, 1x, infinity x we call A. Similarly, let the plane P infinity x infinity z meet the y-axis in a point whose non-homogeneous coordinate in the scale 0y, 1y, infinity y is B, and let the plane P infinity x infinity y meet the z-axis in a point whose non-homogeneous coordinate in the scale 0z, 1z, infinity z is C. The numbers A, B, C are then the non-homogeneous x, y, and z coordinates of the point P. Conversely, any 3 numbers A, B, C determine 3 points A, B, C on the x, y, and z axis respectively, and the 3 planes A infinity y infinity z, B infinity x infinity z, C infinity x infinity y meet in a point P whose coordinates are A, B, C. Thus, every point not on the singular plane of the coordinate system determines and is determined by 3 coordinates. The point P is then represented by the symbol A, B, C. The dual process gives rise to the coordinates of a plane. Point and plane coordinates may then be put into a convenient relation, as was done in the case of point and line coordinates in the plane, thus giving rise to a system of simultaneous point and plane coordinates in space. We will describe the system of plane coordinates with reference to this relation. Given the system of non-homogeneous point coordinates described above, establish in each of the pencils of planes on the lines V, W, U, W, U, V a scale by choosing the plane U, V, W as the 0 plane, 0 sub U equal to 0 sub V equal to 0 sub W in each of the scales, and letting the planes O, V, W, O, U, W, O, U, V be the planes infinity U, infinity V, infinity W, respectively. In the U scale, let the plane through VW be the plane 1 sub U, which meets the x-axis in the point negative 1 sub x. Similarly, let the plane 1 sub V meet the y-axis in the point negative 1 sub y, and let the plane 1 sub W meet the z-axis in the point negative 1 sub z. The U scale, the V scale, and the W scale being now completely determined, any plane pi not on the point O, which is called the singular point of this system of plane coordinates, meets the x, y, and z axis in 3 points L, M, N, which determine in the U, V, W scales planes whose coordinates, let us say, are L, M, N. These 3 numbers are called the non-homogeneous plane coordinates of pi. They completely determine and are completely determined by the plane pi. The plane pi is then denoted by the symbol square brackets LMN. In this system of coordinates, it is now readily seen that the condition that the point ABC beyond the plane LMN is that the relation LA plus MB plus NC plus 1 equals 0 be satisfied. It follows readily, as in the planar case, that the plane LMN meets the x, y, and z axes in points whose coordinates on these axes are -1 divided by L, -1 divided by M, and -1 divided by N, respectively. Footnote: this statement remains valid even if one or two of the numbers LMN are 0. They cannot all be 0 unless the plane in question is the singular plane, which we exclude from consideration, providing the negative reciprocal of 0 be denoted by the symbol infinity. In deriving the above condition, we will suppose that the plane pi equal to LMN does not contain two of the points u, v, w, leaving the other case as an exercise for the reader. Suppose then that u is equal to infinity sub x and v is equal to infinity sub y are not on pi. By projecting the yz plane with u as center upon the plane pi, and then projecting pi with v as center on the xz plane, we obtain the following perspectivities. 0yz is perspective with center u to xyz is perspective with center v to x0z, where xyz represents any point on pi. The product of these two perspectivities is a projectivity between the yz plane and the xz plane, by which the singular line of the former is transformed into the singular line of the latter, denoting the z-coordinate of points in the yz plane by z prime. This projectivity is represented, according to Theorem 8, Corollary 2, and Section 68, by relations of the form equations 1, y equal to a1x plus b1z plus c1, z prime equal to z. We proceed to determine the coefficients a1, b1, c1. The point of intersection of pi with the y-axis is 0, -1 divided by m, 0, and is clearly transformed by the projectivity in question into the point 0, 0, 0. Hence, 1 gives c1 equal to -1 divided by m. The point of intersection of pi with the z-axis is, if n is not equal to 0, 0, 0, -1 divided by n, and is transformed into itself. Hence, 1 gives negative b sub 1 divided by n minus 1 divided by m equals 0, or b sub 1 equal to negative n divided by m. If n is equal to 0, we have at once b sub 1 is equal to 0. Finally, the point of intersection of pi with the x-axis is -1 divided by L, 0, 0, and the transform of the point 0, 0, 0. Hence we have negative a sub 1 divided by L minus 1 divided by m is equal to 0, or a sub 1 is equal to negative L divided by m. Hence, 1 becomes y equal negative L divided by m times x minus n divided by m times z minus 1 divided by m, a relation which must be satisfied by the coordinates x, y, z of any point on pi. This relation is equivalent to Lx plus my plus nz plus 1 is equal to 0. Hence, ABC is on LMN if equation 2, LA plus MB plus NC plus 1 is equal to 0. Conversely, if equation 2 is satisfied by a point ABC, the point 0BC is equal to P is transformed by the projectivity above into A0C equal to Q, and hence the lines PU and QV, which meet in ABC, meet on pi. Definition: an equation which satisfies by all the points x, y, z of a plane and no other points is called the point equation of the plane. Definition: an equation which is satisfied by all the planes u, v, w on a point and by no other planes is called the plane equation of the point. The result of the preceding discussion may then be stated as follows. Theorem 9. The point equation of the plane LMN is Lx plus My plus Nz plus 1 is equal to 0. Theorem 9'. The plane equation of the point ABC is AU plus BV plus CW plus 1 is equal to 0.
Projective Geometry, Volume 1. This book was written by Oswald Veblen and John Wesley Young. It was published by Blaisdell Publishing Company, London, 1910, and is now in the public domain. It is read by Jim Renholt, with programming and illustration by Jim Renholt, 2019. Thank you for listening.